Okay, good morning. So after today, we finished the chapter 1 and chapter 2. From today, we are going to discuss transforms. We are going to discuss two transforms. The first one is the Laplace transform. The second one is Z transform. The Laplace transform applied to continuous time signals, and Z transform applied to discrete signals. So that's the difference. Usually, before Laplace transform, we need to discuss the Fourier transform. Fourier transform, some usually discuss, for example, in math. Anyone knows the Fourier transform in mathematics? No one? Or in signal systems here. But we cannot discuss so many things. But Laplace transform is very important. So instead of Fourier transform, we are going to directly discuss Laplace transform. I will briefly introduce the formula for Fourier transform and also its purpose. Then we are going to go to Laplace transform. So Fourier transform means I have a time domain signal, which is a function of time, continuous. If I multiply by this signal to the negative e to the j omega t, exponential, e to the j omega t. Everybody still remember from Euler's identity, e to the negative j omega t is supposed to be cosine omega t minus j times sin omega t. So that's cosine and sin functions, but complex. Usually just directly e to the j omega t. Then we take the integration for all time negative infinity to positive infinity and with respect to t. And you can see after the evaluation, this t will be gone, right? We have only a function for omega. So we have this one, and capital X corresponding to small x, and with the omega. The t will be, integration variable will be gone, and we have only a function for omega. Some we can write this j omega. That doesn't matter, right? J is constant. So this is called the Fourier transform. So Fourier transform invented by Fourier, right? That's trivial, right? And what's the purpose for this one? Now, we do not discuss a lot of details. I'll just give you a hint. Suppose you have a continuous time signal. For example, if this signal is just the cosine omega t, and we write more in general, so e to the j omega t. And you multiply by this, j omega t, and if you have a frequency positive j omega t, you multiply j omega t, what is this? What do we get this? E to the j omega t positive times e to the negative j omega t, what do we get this? This one will be e to the 0, right? Plus minus. This one means equals 1. And if you take the integral, and also this divided by usually, okay, in mathematics we have a lot of definitions, so we can just use this one. We are going to get a non-zero value to the integration. What this gives us is the frequency component at omega. That means, if, for example, if you cosine, what's this signal here? The power? The angular frequency equals what? 377, right? So this one, 377 t. This is the power line here. What is the AC voltage here? And on the outlet, on the wall. Cosine 377 t, right? Yes? In AC circuit, what is the frequency of here? At your home, what's the frequency here? 60 Hertz, right? 60 Hertz converted into radians per second equals 377, right? if you suppose this one is your xt, right? Then if you use xt times e to the j omega t, then do the integration with respect to t, and this one omega only equal to non-zero value, for example, some value for when frequency equals 377. This one not equal to 0. When omega equals 377. And all others not equal to 377, all this part will be equal to 0. Yeah? If you plug into this, you do the integration, that is in method 168. You can do the integration. You find out that this one equal to 0, except for this frequency. This gives us a hint that this Fourier transform gives us the frequency component at that frequency. If you calculate the Fourier transform of this signal at some frequency, that gives us the frequency component at that frequency. Does this make sense to everybody? All right, now let's check. Suppose you calculate the Fourier transform of this power here. What is this 377 is? I said it's not equal to 0. What is it? That gives us the frequency component at that frequency. Give us the voltage, for example. What is this voltage? 120. So that one will be equal to 120. We know that this is an ideal sinusoidal function. The frequency equals 60 Hz, which equals 377, and its amplitude equals 120. That is what we get. How about 370, 380? Other than this, other frequencies equals what? Equals nothing, right? Because this is ideal. The frequency is only 60 Hz, 377. All other frequencies, the component equal to 0. Right? So that's the only thing you need to know so far. Right? You take the Fourier transform, you get at some frequency, you get the component at that frequency of the analog signal. That's it. But Fourier transform has some limitation. That means if I give you a signal, for example, xt equals ut, it's just constant. For example, we have 5 ut, 5 volt for all this time. If you do the integration, you find out that this does not converge. That means you cannot calculate this. This value can be anything. We do not have a definite value for this. So for this kind of signal, what we want to do is we want to reduce the signal, multiply by some factor that make this convert. And a typical way is I multiply this one e to negative sigma t. You give me this signal. In my example, I said this is 5 ut. 5 ut looks like this, right? 5 ut. And you do the integration, you find, okay, that value equals infinity. Diverge. That means this one does not exist. We cannot do it. What we do is you multiply by e to the negative sigma t. Sigma is a real number here. That means this is an exponentially decreasing function, right? So this one multiplied by this. That's how we draw the signal. Okay, 1 times this one give us something like a value like this. Now this one multiplied by this e to the negative j omega t, possibly and hopefully we can do the integration. What is the physical meaning for the integration? What does the result of the integral give us? Give us the area between the curve and the x-axis, right? So if ut is like this, and you multiply by this one, this is a cosine function. So this result will be like this. Now you calculate this area over here. This does not exist. See, this area can go to infinity. Or even if it is oscillating around here like this, you still cannot calculate the integral. Why? Because this one goes from negative infinity to positive infinity. So all this area add up together equals what? Equals 0 means you will use multiples of the period, right? How about from negative infinity to positive infinity? We don't know that. That is not definite. For example, from here to here, not 0. From here, not 0. Up to this, from here to here, not 0. Up to here, not 0. Okay, up to only this point, equal to 0. But from negative infinity to positive infinity, what is it? We don't know that. Possibly 0, possibly not. Most probably not. So that one does not exist. Instead, I decrease this signal by multiplying it with the exponential decrease. So the signal will be like a decreasing exponentially. Then this signal will be like this. Now you do the integration. We may find that the integral converge. That means the area approaches some value that we can calculate. So that is the purpose for Laplace transform. So basically, Laplace transform is a special Fourier transform. Fourier transform, you just use the given analog signal, multiply e to the j omega t, do the integration. But the Laplace transform, you multiply by e to the negative sigma t first, then do the integration. So this is a Fourier transform. And the Laplace transform is, you give me this one, the signal, I multiply e to the sigma t first to make this easily converge. Then do the Laplace transform. Then that means we do the integration from negative infinity to positive infinity. Does it make sense to you? Fourier transform, you just use the original signal, multiply with this, then do the integration. And we discussed the physical meaning for that, so we ignore the details. But sometimes, most probably, this does not converge. So what we do, our technique is you make this signal attenuate more, multiply by exponentially decreasing function. Then this one will be smaller, in some sense. Then do the Laplace transform. And let's see, although we do this, we do the Laplace Fourier transform of this signal. I want to observe and to check. I still want this signal here, but I will combine these two terms together. Instead of do this first, I will do this first. Doesn't matter, right? What property is this? I can multiply this first, or I can do this first. What property is this? Two times 3 times 4. I can do this first, equals 24. 6 times 4. Or I can do this first. 2 times 12 equals 24. What property is this?
The property is associative.
Associative, right? Okay, so I will use this one and multiply this first. So instead of this 2, I will do this 2 first. E to the negative sigma t, e to the negative j omega t will be equals to negative sigma plus j omega then times t, then dt. That's nothing, just mathematical manipulation. Now compare this one with the Laplace transform. What's the difference? This part is the same, this part is the same, integral the same, dt is the same. The only difference is this one multiplied by this number is imaginary number, negative j omega. But here, this one, what's this? This is a real number. We have sigma, we have j omega. So that's the only difference. We do not like this lengthy writing. Okay, instead we give it a small. We give this simple. So we call this one e to the negative st. So we write this part as a s. S is a complex number, has a real part and the imaginary part. Then that's dt. That is the definition for Laplace transform. We discussed the purpose for this one. We want to make more signals the integral of more signals to converge. So we multiply the original signal with a decreasing exponential function. Or we can just use this original signal multiplied by e to the negative st, then do the integration, just like a Fourier transform. But instead of negative j omega, which is imaginary only, this one is real. This is complex. We have a real, we have an imaginary. That's it. That's the formula for Laplace transform. Eh? Any questions on this? So if I give you a signal xt, can you calculate the Laplace transform? That is just only a math, right? For example, I'll give you a xt equals 1. Can you do this, evaluate the integral? Everybody can do this? This is in math 168, right? We have two definitions, two types of Laplace transform. Right? This is called two-sided. This is called two-sided. Why is it called two-sided? Because we do the integral from negative infinity to positive infinity. Or we can define a one-sided. Right? So one-sided. What is one-sided? Only one side. Right? So this integral equals from 0 to infinity, and xt times e to the negative st then dt. So instead from negative infinity to positive infinity, we only evaluate from 0 to the right. Right? So that is called one-sided Laplace transform. Based on different situations, applications, sometimes we want one-sided, sometimes we want two-sided, and sometimes one-sided and two-sided are the same. Right?
So,
yes.
So again, what exactly are we trying to do with this transform?
The transform is convert a time domain signal, right? I'll give you xt. You need to know the xt. Before you do this, I'll tell you what xt is. Then, mathematically, you just multiply this by e to the st, then do the integration. That is mathematics. Mathematics just said, okay, that's it. But the engineering, engineers, technologists, we need to know what's the physical meaning of this. You do this, what does that mean? That means we try to find the frequency component of that signal at that frequency. Like in Fourier transform. Fourier transform, mathematicians just said, okay, you give me a signal, no matter it's t or not, they don't care. Usually they said, use fx. In mathematicians, they do not use t most of the time. They just use fx. Right? Then e to the j omega x, then dx. They do this. What is fx? Any function. Who cares? But in engineering, we said this t is a function of t. That means it is a signal. Right? The signal has a frequency, right? My DC signal or AC signal has a frequency. So what we do is, if you change this one into a t, you change this into t, what is this omega? This omega is the frequency. This gives us the component of ft at this frequency. As in this example, if you said ft equals 120 cosine 370, that is engineering signal here, right? Then what we do, what we can get from this Fourier transform, you don't need to evaluate because we know the physical meaning for this. Right? So this one will give us f377. That means the frequency component when the frequency equals 60 Hertz. That definitely should be equals 120 because we know the frequency component is 120. If you do this mathematically, you need to get this result. If not, you are wrong. Because we know that. Does it make sense? Or if I ask you, how about the 477? You plug this one into the calculation, you get some result, right? We engineers, we don't need to calculate for this example. We said, okay, that equals 0. Why? Because this one is an ideal cosine function. It has only singular frequency, which is at 60 Hertz. Other than 60 Hertz, nothing exists. So you give me this frequency, nothing. You need to get 0. If it's not 0, your calculation is wrong. Does it make sense? So that is the physical meaning for Fourier transform. So we know how to do it, and we know what it means. So that's the difference between engineers and mathematicians. Mathematicians, they just calculate all this value. They don't need to care what your result is. We need to know the meaning of this. But for Laplace transform, it will be more general. Instead of give us only this frequency, it gives us a sigma plus j omega. It gives us also some another function. This one is attenuation. We are going to discuss more. This one is more difficult to understand. We know this one is frequency, it's easy to understand, but this one is the attenuation factor. If you study, for example, control systems later in 477 or 478, you may want to know this, what this sigma is. If you study 412, later time NAET, you need to study 412. This one means the attenuation. This term is related to the attenuation. For example, if you have this circuit, the frequency is determined by L and C. This attenuation, because if you have a source, for example here, you apply this source initial condition. Later time, this one, the energy will be 0, right? Because all the energy back and forth will be dissipated on this one as a form of heat. So this one will be gone. Right? This term is related to the R also. Right? So we have a lot of physical meanings for this based on different applications in circuit analysis, in control systems, or in any engineering second order circuit, even first order. We are going to know this later time. So far, we don't care all this. You just say, okay, that is just the S. S is a real number. Is complex number. Does that make sense? Right. So at least you can calculate the Laplace transform, right? You close your eyes. I give you this signal. You just do the integration. That's it. Any questions on this?
So is that S going to be given?
S, no, S is not given. S is any number you choose. Like, for example, in this J omega, I said, okay, omega equals 377. For example, if I ask you, I tell you omega equals 377, you calculate that equals 120. I calculate, okay, what is when omega equals 400? You give me the result equals 0. Right? But if I only give you a signal like this, I ask you to analyze the signal. You need to calculate the frequency from 0 to all possible frequencies. You just tell me, okay, when omega equals 0, my result equals 0. That means that is not DC. When omega equals 1, right, that result also equals 0. That means there's no frequency component, the frequency equals 1. There's no there. You calculate all of this, you find out, okay, only when omega equals 377, I get a non-zero value which equals 120. All others equal to 0. So that is analysis of the signal. Okay? So Laplace transform or Fourier transform actually is the analysis of a signal. Try to find the frequency component. Does that make sense? I'll give you a time domain signal. I ask you, what signal is this? What kind of frequency is inside? You use a Fourier transform. Right? You ask yourself, how about the frequency equals 100? You calculate. You get nothing, that means there's no frequency 100 inside. Alright? Then you calculate the frequency equals 101. You get nothing, then that means there's no frequency 101 inside. You do all these frequencies, you get the property of the signal. Does it make sense? Okay. Now, we know the Laplace transform is this one. We are going to write this one as a function of what? Like in this here, the function of omega, right? Where does the t go? The t is gone, right? Why is this gone? Because this one is the integration variable. After the integration, this t is not there anymore. So what function is this? This t is gone. This t is gone too, right? So this one will be a function of capital X, right? That's related to the x. This is time domain. We use a small letter. In frequency domain, we use capital letter, right? And this one is a function for s. You do this integration, you get this one. Any question on that? Can I give you a problem to solve this one? All right, let's do it. Example. I give you a signal xt equals e to the negative at ut. A is constant. What is this one? What is this? This is time domain signal, right? We can plot this. And what I want is a Laplace transform. How to do this? So the Laplace transform equals definition. Anyone?
The
Integral.
negative infinity.
Negative infinity, positive infinity, xt e negative st dt. That is only the copy of the formulas, right? That's the first step. Okay, now let's do this. Copy this, we plug into xt. Xt is given, right? That equals e to negative at ut and dt. Oh, sorry. Like this. And e to negative st and dt. Everything's good so far? Alright, now we do this. This function times this function times this function. Right? Just as a very beginning, we need to draw this, and then multiply together. This ut only exists when t is greater or equal to 0, right? Ut look like this. So that means all the values for negative time will be equal to 0. So this one will be, although it's from negative infinity to positive infinity, do I need to care about the negative values? No, because this part has no negative value. For any negative time, this one will be equal to 0. Yes? Alright, so this one will be 0 to infinity. When t is between 0 and infinity, what is ut? 1. Alright, 1 I don't need to write, right? Alright, so that is only this one, negative at times e to the negative st dt. Ut is just 1. Good? Alright, now let's do more. 0, infinity. These two, just like here, right? So multiply together. That will be equals e to the negative. You need to know how to do this math. E to the negative, combine these two terms. S plus A. Is this S plus A times T? Yes or no? E to the negative AT times E to the negative ST. Is this one E to the negative S plus A times T? Yes, right? Okay, then dt. Right, now we need to use techniques we learned in Math 168 to this integral. E to the negative A, for example, let me get one. E to the lambda t dt. What is this? How to do the integral of this?
Isn't it just lambda t?
That one equals what?
Lambda t.
E to the lambda t, right? Do we have anything in front?
Lambda t.
1 over lambda, right? Hello? Say yes or say no.
Yes.
Yes, right? Because when we take the integral of this one, equals itself multiplied by lambda. Lambda cancel to give us this. Okay, so this. Now, our is e to negative s plus a times t dt. So this, that means this one equals negative s plus a, this one, lambda, right? So lambda is equal to this part. And e to the negative s plus a t. Right? Okay, so I copy, I remove all this. Right? And this one equals negative 1 s plus a and e to the negative s plus a times t.
Over
0.
0
Infinity. Right? Okay, I don't like this negative here. A lot of negative make me dizzy, right? Okay, so I need to switch this part, right? 0, infinity. Good, right? Right? What is this? S plus a, 1. When t equals 0, what's this? This one equals 0. E to the 0 equals 1. Minus, when t equals infinity, what is this part? Okay, we need to consider, right? Not necessarily we can do this. If s plus a greater than 0, that means this one is a negative number here. Then when t equals infinity, what is it? This one is negative number. For example, e to the negative 5t. When t equals infinity, what is this value? Huh? 0, right? Because this one is exponentially decreasing. The draw is like this, right? When t goes to infinity, that equal to 0, right? Okay, so this one equal to 0 here, right? So 1 minus 0 equals 1. Okay, so that equals this, means when f plus a greater than 0. Good, right? How about s plus a is less than or equal to 0? That means it looks like a negative 5t, okay, when t is less than or equal to 0. Right? When less than 0, because when equal to 0, we already equal 0. So when this one negative infinity, like this, negative, this is positive. Right? If this one is less than 0, that means this is positive. Positive, that means, for example, 5t. When t equals infinity, what is this? This equals infinity, right? Okay, infinity, that means downward, not convert. So we cannot do that. So this one does not exist. Does not exist. We don't care. We only care real things in engineering. So that's why equals this for this one. Maybe even greater or equal to 0. Actually, only equal to 0, greater than 0, right? If equal to 0, then this equals to 1. Any questions on that? So that's it. That's the Laplace transform. We already calculated it. Right. Right. Another example is, for example, if xt equals e to the 3t ut. What is this one? E to the 3t times ut. What is it? A is given, right? That's a special case of that one. So can you tell me what is the Laplace transform for this one?
3.
S plus A. What is A here?
3.
3 or negative 3? A equals 3 or negative 3? Negative 3, well, because here it is negative A. So negative A equals 3, so that's A equals negative 3. So the Laplace transform will be S minus 3. And S can only be this one greater than 0, that means S greater than negative A. Means X greater than negative 3. So that will be a positive 3, right? Right. So when S is greater than 3, Laplace transform equals this. How about less than 3?
Doesn't make sense.
No Laplace transform, does not exist. Right. This is called the region of convergence. That means all this signal only converge when S is greater than 3. So this is called the region of convergence. Yes? Huh? Pardon?
Another problem.
Give you another problem? Oh yeah? Another one is, for example, said use a signal, give you, still use x. Xt equals e to the t. Is e to the negative t, ut. What is the Laplace transform of this? What is this one?
1 over
S plus 1.
S plus 1?
1 over S plus
1 over S plus 1?
1. When S is greater.
So equals 1 over S plus 1? Yes or no? Yes, right? And this one is good, but you also need to specify the region for convergence because S cannot be anything. Right? So S must be greater than negative 1. Make sense? So for this kind of exponential signal, the Laplace transform, we already know that. So this one here, you need to memorize. S e to the negative A, the Laplace transform is 1 over F plus A. That's very typical, because we are going to deal with a lot of exponential functions. Any question on this? Right. Now we know SF is a polynomial, look like this, in terms of S, right? So this one equals 1 over S plus 1. So in general, this can be represented by a numerator divided by denominator. And both are functions of S. In this example, the numerator equals 1. The denominator equals S plus 1. And we are going to find the zeros of XS. What is the zeros of this? We are going to make S and S equal to 0. Then you solve S1, S2, and all these rows. You make the top numerator, this polynomial, into equal to 0. You find the solutions, S1, S2, S maybe more. Those are the zeros of this one. Why it's called zeros? That means if you plug S equal to this S1, S2, or this one, this XS will be equal to 0. And poles of this how to find the poles of this, right? Then that one will be the denominator equal to 0, right? And you're going to get P1, okay, P2, and so on. All these are root of this denominator. But this one, if you plug S equals this P1, P2, all these solutions, it will make this part equal to 0. Eh? If you make this one equal to 0, that means this one will go to infinity. So that is called the poles. Questions on this? Before we have an example. Right? Suppose xs equals s squared plus 3s plus 2 and s squared s plus 1. S squared plus 5s. I'll give you this Laplace transform. What are the poles? What are the zeros? What we want is the zeros first. The zeros is the value of s that make this one equal to 0. That means make the top equal to 0. Right? So how we do this? We are going to s squared plus 3s plus 2 make this one equal to 0. And we solve this equation. You use any technique you can do it. Quadratic formula, factorization, or no matter what, that's not the topic in this class. So this one, I will prefer use a factor for this. So that one will be s plus 1 times s plus 2 equal to 0. Right? I factorize this, that's equal to this one. Right? So that means the zeros s1 equal to -1, perfect. Right? And s2 equals -2. So I have 2 zeros. What does that mean? That means if you plug s equals -1 into here, you make this one equal to 0. And if you plug s equals -2 inside here, this one also equal to 0. So that's why both are called zeros of the Laplace transform. Next one, we calculate the poles. What are poles? Poles, that means the s value that make this one goes to infinity. That means we need to solve this one to make this equal to 0, right? That one will be s squared plus 5s equal to 0. What does that mean? Usually 0, so you can use z1, z1 and z2. So to distinguish this, right? This is better way. I think in the slide we use z1 and z2. What are the solutions for this? Again, you factorize this. S squared plus 5s equals s times s plus 5, right? Right? Make this one equal to 0. So s equals to 0, s equals to -5. Right? So we get P1 equal to 0 and P2 equal to -5. Again, we have 2 poles. One is at 0, another one is -5. That is how we calculate the zeros and the poles of a Laplace transform if we are given that Laplace transform. Alright, now look at this example. What is the 0? What is the 0 of this?
-1.
-1. If you make x equals -1, is this one equal to 0?
0 would be. They don't have a.
are on.
Okay, this one has no zero.
Yeah, no zeros.
You cannot choose any s to make this one equal to 0. So this one has no zeros.
Yeah, the pole is negative.
Right? Do we have poles here?
Yeah.
Yes. Which one?
-1.
-1. Right? We need to draw this zero poles plot. Right? How to draw this? So it's called zero pole plot. For this example, -1 is here. It's -1, -1, -2, and 0, and -5. Right? What I do is 0, I will use a circle. This one is -1, right? And -2. So I will use this negative. Represent. This one is 0, this one is 0. And this 0 here is, what is this? That is a pole, right? And pole, I will use a cross to represent. Question on this?
Wait, what's the cross for?
The cross means a pole. Right? So we have two poles, one is at 0, so at 0, cross. Another one is at -5, you cross. Good?
Okay, but what is that?
This is called zero pole plot.
Oh, what, like,
What is the purpose for this? Alright? For example, I want to design a control system. I want this one at some point, some frequency, have what kind of gain or anything. I give you my requirement. How are you going to design, implement this? You first one, you need to write out this formula, this Laplace transform. How? Right? You need from the post. Then you write this one. Then you solve that. Right? So that is the purpose. We are going to discuss later time. I cannot tell you all this. You are going to confuse. So now, if I give you the Laplace transform, you need to know how to plot the zero and the pole plot. That's the only thing you need to know right now.
so, is that supposed to be like the graph of like specific frequencies that,
Yes, that is the physical meaning.
So-
Specific frequencies and the attenuation for sigma. Because the S, this one is very special. Because you can see all are real, right? Actually, there must be a real number, a complex number. Means these poles cannot be on here. Must be somewhere between this. On the whole plane, two-dimensional plane. Some real part and imaginary part. Right? I'll give you an example later. Alright, so this example is I give you the Laplace transform. You need to know how to calculate the poles and the zeros. And you need to know how to plot this. Any questions on this? Can you do this? Yes, right? You calculate the poles, zeros, you plot on the plot. That's it. As we said, you just mentioned, why this is useful? Okay, we need to go inverse, reverse. If you know these poles, zero and pole plot, can you write out this Laplace transform? For example, I'll give you this one. I ask you to write the Laplace, don't let you see this, but I ask you to write the Laplace transform. That's easy, right? So the Laplace transform will be equal to, we start from here. The root is 0, but this is a pole. So there must be s minus 0 here on the bottom. Right? This one is a 0, which equals -1. So that means s minus -1 here on the top. Right? S minus -1, actually s plus 1. Right? And this one is another 0. So that will be s minus -2 here on the top. And this one is a pole, so it will be on the bottom. So that will be s minus -5. Oh, maybe some constant again at the beginning, so you just put a constant. Right? This one is exactly equals 1. For example, if I said 10 here, this information is not represented in this plot, but so that's why we put a constant here. But the constant, as we said, we don't care, right? You can use an amplifier, change this constant to anywhere. Right, so what is this? This one is k times s plus 1 times s plus 2 and s times s plus 5. Is this one equals this? Yes. So you need to be able to go back and forth.
So to get the time domain signal, we...
No, we are not discussing. See, on this slide we don't have any time. We don't have any t here. We only discuss the Laplace domain. We only discuss everything is on the S plane. So this is zero plot in the S plane. Right? There's no time. Do we see any time here? No time. We are talking things here in frequency domain, in S domain, not in time. Any question on this? Okay, so in general, if I give you a zero pole plot, what is the general form of the Laplace transform? Right? So in general, the Laplace transform will be, there's a constant here. I don't know. This one is not reflected here. Here, on the top is s minus the first zero. Right? The first zero is z1. Right? Maybe we have another zero, z2, and we may have more. I don't know. Given, right? And on the bottom, that will be s minus the first pole, p1, and times s minus p2, and maybe more. This is, we can get this from the zero pole plot. Any question before I give you a question for exercise? Everything's good here? xs equals, in the slide this is the fx, that's going to matter. K times s plus 1.5 s plus 1 plus 2j s plus 1 minus 2j over s plus 2.5 s minus 2 s minus 1 minus j s minus 1 minus j. That is the Laplace transform. So this example is very simple because all are real, right? Actually, they must be complex. So now you can see we have complex poles and complex zeros. Okay, I want you to draw the zero and the pole plot. Okay? Yes?
In the numerator, the second thing is that
S plus 2.5.
No, in the top.
This one?
Yeah.
S plus 1.5. That times S plus 1 plus 2j. This one is S plus 1 minus 2j. This one is S minus 2. This one is S minus 1 minus j. This one is S minus 1. Okay, plus. That's not. So I would like plus j here. I need somebody to plot this on this plane. The easy part is the poles on zeros I already calculated for you. You don't need to calculate it. You only need to draw here. The zeros are and the poles are very straightforward. Okay, let's see What is the first zero?
Negative 1.5.
Negative 1.5. Where should I put that? Here, right? Okay, the negative 1, negative 2, so this one is here. Like this? I need to put a 0 here, right? That means this is negative 1, negative 2, like this. That's perfect, right? Negative 1.5. What is next 0?
Negative 1, negative 2j.
Negative 1 minus 2j, right? Negative 1, negative 2j. Okay, question is how do I plot that?
Negative 1.
Negative 1 is here,
And
the negative 2j is here, right? So negative 1, negative 2, okay, so it's here. Everybody got this? Any question on this? So that is negative 1, negative 2j, right? So that's negative 1, negative 2.
So the y-axis is the j-axis.
Yeah, this is a complex plane. So this is real, this is imaginary. Right? Real is on this way, imaginary is on this way, right? That is in trigonometry, right? Yes or no? Polar system. Right? And this is the real part of F, and this one is the imaginary part of F. If you look at the textbook or the reference, this is the real part, this one is. What is the real part of S? What is the real part of S? Sigma, right? Eh? What is the imaginary part of S?
Here's j.
Omega, right? Eh? That means this direction gives us the frequency information, this direction gives us the attenuation. Eh? That's your physical meaning come to you slowly. Eh? We cannot do too fast. Alright, so this one, there must be a complex conjugate. If you have 1 here, there must be something on top.
So negative 1.
So negative 1 plus 2j, right? 1, 2 here. This one. Like this. Good? Everybody get this? And you need to ask if you have a question. Okay, now we finish all 3 zeros, right? Next one is the pole. What's the first pole? Negative 2.5, perfect. Okay, so negative 3 is here, so this one. How to draw this?
It's going to be an x.
Huh?
It's going to be an
X,
x.
okay, cross. Perfect. What's next to 0?
Column 2.
Positive 2, right? 1, 2 is here, so that's cross. Do we have any other poles? What's the other?
Positive 1 plus 1j.
1 plus j. So where is it? 1 plus j is here, right? Here. What's the next one? 1 minus j, right? Okay, 1 minus j is here. Right, that's it. I'll give you this Laplace transform, you can plot this one. That's easy, right? Right. This one will go this way. Right? Now if I give you this one, can you go that way? Yes, that's the same thing, right? This one is 0, so negative 0.5, so that will be s plus 1.5 on the top. This one is 0, right? The 0 is 1, negative 1 minus 2j, so that will be s plus 1 plus 2j. And so you can do this one by one, you get this. A few minutes to think about this. Yes.
How did you plot the first pole?
The first pole. This one.
Yes.
This one is, see, f plus 2.5 must be equal to 0, right? That's the definition for pole. So that means this solution equals negative 2.5. So negative 2.5. This is negative 1, negative 2. This is only real,
Okay, I did the A first.
right? So must be on this here. Because there's only real part. So that will be at this point. Any further questions? Everything's good here? Okay. When we calculate the Laplace transform, we can, you are given the time domain signal xt, you calculate the capital Xs. Right? Next class, we are going to discuss how to calculate that. Today, we only discuss the definition or the basics of Laplace transform. Once we have this Laplace transform, no matter how you get this, we need to specify the region of convergence. That is also important. If you do not specify the region of convergence, that is not complete. Like in difference equation or differential equation. Only the difference or differential equation cannot guarantee the uniqueness of the system. We need the initial conditions. Remember, we have example of that, right? If your initial conditions is not initially at rest, then this system may be non-causal or maybe not unique. Right? This same thing here. Once we get to the Laplace transform, we need to specify the region of convergence. Like in this example, just erase the region of convergence must be f greater than negative a. If your f is less than negative a, then that integration does not exist. You cannot give me that. You cannot do it. The region of convergence. So what is the meaning of, what is the physical meaning for region of convergence? The physical meaning for region of convergence means if your x, your s is in that region, then you guaranteed to get a converged Laplace transform. That is sigma. This is omega, or we can write j omega. That doesn't matter, right? The region of convergence will be the area that make the Laplace transform converge. And this one must be, this is called S-plane. Must be some region on the S-plane. So what kind of region? Must be half plane. Must be planes of cut like this. Cannot be any other shapes. Cannot be a circle. Cannot be like a triangle. Must be vertically cut. For example, I said the region of convergence is this side. That is okay, possible. Or the region of convergence is this side. Right? That is also possible. But like I said, okay, the region of convergence is inside this one. Right? There is no way for this one. For Laplace transform, the region of convergence must be like this, to the right or to the left. or some special case can be the whole plane. For example, if the equals 1, what is the region of convergence? That means what else can make this one converge? What else can make this one valid?
Everything.
Everything, right? No matter s equals what, because this one is constant. S equals 1, still equals 1. S equals 10, still equals 1. So no matter what your s is, so this one is always like this. So this means the region of convergence is the whole plane, including 0, including infinity, anyway. Right? So that, how about if this one equals s? What is the region of convergence for this one? How about 1? How about equals 100? Works? Works, right? How about 1000? Works.
Everything greater than 0.
Less than infinity, right? If you said s equals infinity, no, because this one equals infinity. Remember this one, how we get this one? This one is integral. So this one equals something integral, something dt, right? And you said this one equals infinity. No, you cannot do that, right? So in this case, if this one integral equals s, that means this s must be less than infinity. Cannot be equal to infinity. Right? So if your Laplace transform equals this, then the region of convergence equals just the s not equals infinity. Anywhere else is good. 1 million, 1 million, that's perfect. But only not equal to infinity. Is it good here? In this one here, we have a lot of zeros. And we have some poles, not like as simple as this one. How to determine the region of convergence for this one? Okay, the rule is the region of convergence is the area, is the plane, half plane, on the 0 and the pole plot to the right of the rightmost poles. The rightmost pole. To the right of the rightmost pole. The region of convergence is the half plane on the 0 and the pole plot to the right of the rightmost pole. For this example, what is the region of convergence? Everything greater than 2, right? We don't care about the zeros. So in this case, we don't care about the zeros, right? Only because zeros always converge. Because if your s equals this one, if your s equals this, what is your sf? What is this? If your s equals this point, what is this value? Equals 0, because this is 0, right? 0 makes this one equal 0. So all the zeros is good. So we don't care, right? Actually, we care about the poles. The region of convergence is the right plane to the right of the rightmost pole. This one here, this one is rightmost. So the region of convergence will be sigma. The sigma with the s absolute value greater than 2. Can this one equal to 2? No, cannot. Right? We already showed before that it cannot be equal to 2. Greater than 2. Any questions on this? There's a lot of things you need to memorize. Before that, it's better you understand it. So that means if you give me any value here, for example, this one equals 5. This one here, 5. S equals 5. What is S5? Can you give me a number? Does this exist? Yes, right? Because it is in the region of convergence. Maybe equals 1, maybe equals 2, maybe any number, but definitely less than infinity. So that means this one exists. Right. How about this one? This one is 5 plus 2j. 5 plus 2j is here, for example, here. What is this value? Does this exist? Yes, because this one is also in the region of convergence. Region of convergence all the way to the right from this point, from this point. So this one, if you evaluate this, definitely you are going to get some number. This one, converge, does exist. How about this one, here? This one does equals to infinity, right? So this part does not exist. This one exists here, but in this one you cannot see all here exist because this one does not exist. This one does not exist. This one does not exist. Okay, we know the region of convergence is half plane on the S plane, always to the right, always to the right, right? Then we are going to have two situations. The first one is this j omega axis is in the plane. The first one is j omega axis is in region of convergence, like this. Your region of convergence is all the way to like this, to the right, right? So for example, your pole is here. Your pole is here, start. And this one is j omega, this one is sigma. This situation. That means this axis is included the region of convergence. Now look at any S on this plane. Suppose this is S. What is this S? S equals what? This S is a complex number, right? Has a real part plus imaginary part. For example, this equals J10. Suppose this equals 10. What is the real? 0. Well, 0 plus this, right? Any point on the j omega axis, the real part equal to 0. Right? Now we see. We imagine the formula. E to the xt, e to the negative sigma plus j omega t, and then dt. This gives us the Laplace transform. Now, on this axis, all the sigma equal to 0. So this one will be gone. What is this? Fourier transform, right? This one reduced to Fourier transform. So that means if your region of convergence includes the j omega axis, then the Fourier transform exists. Because we can evaluate this. Because this is in the region of convergence. Right? In this case, the second situation is j omega axis is not in the region for convergence. So like this. The region of convergence is this, for example, this 3. Always to the right, right? This one is j omega, like this one. In this case, we do have a Laplace transform existing in this area, but we don't have a Fourier transform because Fourier transform is only on this axis. And that actually is the purpose for our Laplace transform, because we want to calculate the Fourier transform, the transform of a signal when the Fourier transform does not exist. So this one, the Fourier transform does not exist, but the Laplace transform does exist. So that is realized our purpose. But this one, both Laplace transform and Fourier transform exist. Any questions on this? Okay, so what we need to know today is the definition for Laplace transform. Everyone still remember that? Xt times e to the negative st integration from negative infinity to positive infinity. That's for double-sided Laplace transform. From 0 to infinity, that is one-sided. Right? And also we discussed how to calculate the zeros and the poles of the Laplace transform. What is the zeros? The zeros is the solution of the polynomial make the numerator equal to 0. You solve that polynomial equation, then you get the zeros. The poles are opposite, are the zeros or are the solutions for the denominator polynomial. Right? So if you are given a Laplace transform, then you can calculate the zeros and the poles. Once you get all these zeros and poles, you need to be able to plot this on the zero and the pole plot. The zeros are represented by that dot with a circle, 0, right? Circle means 0. And the poles are represented by that point with a cross. So if you are given the Laplace transform, you need to know how to plot this 0 and pole plot. Or inversely, if you know I'll give you the plot, you need to be able to give me the Laplace transform. Except there's a constant before that, no one knows that. You don't care that constant. You only need to give me the zeros and the poles. So you can write out the Laplace transform. All these are fundamentals for later time system analysis with the transform analysis. So today, again, you have good questions. This purpose is not only draw this is only the tools. Later time we are going to use this. Right? Maybe in this class, we don't discuss a lot of details in this class because that's too much. But high level class, as a 412, and or even 477, 478, when you design systems, you need to use this. The next concept is the region of convergence. The region of convergence is the region that if the S is inside that area, the Laplace transform exists. If you give me the region of convergence, then you pick any point in the region, S make F equal that value, you can evaluate the Laplace transform. Outside that region does not exist. Right? And how to determine, so if you calculate the Laplace transform, keep in mind, you always need to give me the region of convergence. Otherwise, you are going to minus some point. And because that's not unique. A later time, we will use more examples you can show. For the same Laplace transform, S, for example, this 1 over S plus A. This one can be greater than negative A, that's possible. And this one less than negative also possible. So this one and this one represent different signals. One is to the right, another one is to the left. Although their Laplace transform are the same, but they have different region of convergence, so they represent different signals. Right? You need to give me both. And if you have complex signals like this, you have a lot of zeros and poles. Right? The region of convergence is to the right of the rightmost pole. Right? So keep this in mind. Any other questions? So next time we will continue to discuss how to the Laplace transform properties and how to calculate the Laplace transform. We are going to use twice to do this. Right? 2 lectures to do this Laplace transform. Because this is important. If you are in ET, you are going to use this a lot in 412 to analyze systems. So this you need to be able to do this. Okay, thanks.